So let's talk about stress. This is how you were probably introduced to stress, right? And the first day of mechanics, probably, or first week of mechanics course, right? That stress is a force divided by some area. And I think later you learn that it's not just a scalar thing, but when you look at that equation, it appears like it's a scalar, right? Like it's just one value. Right? But we know force is a vector. So if I take a vector F and I divide it by a scalar A, what do I have? I still have a vector, right? So it can't just be a scalar. And in the case of this particular problem, it's actually not a scalar. We know it's not a scalar. It's just that all the other entries are zero, and so we can describe the full state of stress with just the one term. Okay. But what stress really is what stress is, right, it's a force that acts upon some area. And really, stress is a point-wise quantity, meaning we idealize a body as a continuum, and mathematically what that means is there's an infinite number of little points, right? So if I were to fill up this whole cylinder with points, and I could draw an infinite number of them, right? Each little individual point would have its own value of stress. Okay? Its own characteristic value of stress. Now it turns out, in the case that I've drawn, the stress is uniform everywhere. Okay? So in this case, they would all be the same value, and therefore we can write this nice pretty equation. Okay? But I chose this A very carefully to be a perfect cross-section of this cylinder perpendicular to its axis, right? What if I wanted to know the stress on a plane that sliced through at an angle? Right? So now I have something like this, where this is a different area, say A prime. What's the stress there? The force is the same. The area is different, right? So you would conclude that I have a different stress. But I haven't changed the size of the sample. I haven't changed the force, right? So it's clear that something weird is going on, or something, there's more we don't know and we need to understand, okay? Or we need to know more mathematics to understand the full state of stress. And it turns out that the stress is different depending upon your choice of coordinate system. And so this was all this, we talked about transformations a minute ago, and now we're going to see how we can use them to understand what the state of stress is. So the state of stress is dependent upon the area in which you choose to normalize the force, okay? And how we define that area can be dependent upon different things, okay? So let's imagine that we have a big slice of the crust of the Earth. Okay? And since we're just sort of removing this one little chunk, there's some external forces applied to this guy. Okay, so these are just some external forces. And again, we normalize them by some area. So these are called, in the drawing that I have, as I have it drawn, we'd call these surface forces, or also known as tractions. You might hear the word traction. So a traction is like a stress vector, okay? It has a direction. It's a vector. It has a direction, okay? But it's divided by some normalized area, okay? And there's also other types of forces called body forces. So if I had some little idealistic infinitesimally small cube in the center of this guy, you know, gravity would act on that thing. And so the gravity would create its own body force, right? Its own force, okay? So if I took this little cube and I pulled it out into a coordinate system that I define, right? I'm the modeler. I get to choose the coordinate system. So I'm going to choose a coordinate system that's x1, x2, x3, okay? And my little cube is sitting here. All right. And because I pulled it out of my plate, right, my crustal plate, which is under some stress, right? We talked about why that may be. It could be at the boundaries. There's the one plate is subsiding, which causes friction. It's pushing on the plate. It could be due to the divergent ridge, you know, where some new magma's pushing up, and it's pushing my plate, squeezing it, compressing it, whatever. So when I pull out my little cube, there's some tractions acting on it, right? They're acting on it. So I'm going to call this guy T, and it's a vector. And just to keep things straight and very, very explicit, I'm going to say that T, it's not necessarily normal to that face, okay? But the normal vector to that face, I'll write as E2. Well, I'll write it as E2. Okay, so this is a little unit vector, E2, that defines the normal to this face. Okay, so when I write my traction over here, I'll write it as T in the E2 direction. Okay, likewise, there's some T in the E3, where E3 is the normal vector that defines this face. Okay. And then you have E1 that defines this face, and it also has a traction. Okay. So now what I'm not drawing just because the figure is going to get too busy, but this little cube is in equilibrium, right? Sum of the forces must equal 0. So it's in equilibrium. So if I've got 3 tractions on these faces, there's got to be equal and opposite tractions on the other faces, right? So I'm not going to draw them all, but something like there'd be a T here. Well, I'll just draw them, but understand. Figure's going to get pretty busy. Right, so these are the negatives of the tractions that I drew on the front faces. Okay? All right. So the last thing I'm going to draw on this figure, and then we'll get rid of it, is now I want to slice my little cube into a tetrahedron. So I'm going to take a slice like this across my cube. So that's what's left is a tetrahedron. Okay? Everybody okay with what I did? All right. And now we're going to clean it up like that. Okay? So there you have the negative tractions on the back surfaces. Since the whole thing's in equilibrium, there's some traction associated with this full face, Tn, and n is defined by the normal vector to this surface, okay? This surface has unit area dA, and the whole tetrahedron itself has a mass dm, okay? So the mass of anything is the density times its volume, dV, okay? So if you don't know anything else in mechanics, where do you start? What's sort of the fundamental rule of mechanics, law of mechanics? This guy Isaac Newton came up. It's attributed to him, right? F equals ma. Right? Technically, you might say that that's the conservation of linear momentum, right? But F equals ma. If you don't know anything else in mechanics, just start with F equals ma and see what you can do. Okay? So we're going to write down, we know the forces, right? Again, these are tractions, so they're forces per area. But we can compute the areas. So then we can multiply the force per area times its area, and then we'll have a force. And then we just sum them all up. It gives us the total force on the body. And then we equate that with ma. Okay? So a couple of things. We have this unit vector n here. So n we'll try to write in black and highlight in other colors, but n is made up of components n1, n2, n3, right? And what those components are the cosine of n with the x1 axis, right? And the cosine of n with the x2 axis, and the cosine of n with the x3 axis. Okay. And then also just geometry. So again, this may seem complicated, but we're not using anything but geometry and F equals ma. Okay? So from geometry, you know, we just already sort of covered it, but like if you had this guy and it had some angle theta with length L, its projection down onto this axis is L cosine theta, right? That actually holds for areas as well. So now instead of a line, if I had an area, here, and then I project it down onto this plane so that I'm interested in this area. All right, so if the original area is A, and then the area in the blue is AP, then we can use the same kind of geometry that it's the original area times the cosine of theta. Okay? So with that, let's write F equals ma. All right. So the first force I have is Tn. So this is the traction vector associated with the face N, and it has area dA, right? So traction vectors are forces per unit area, and multiply by the area that gives me force. Okay, that's a force, right? So that's a positive. Then I have the minus T E1 times N2 dA. And the N2 dA, remember N2 is the cosine, so it's sort of playing this role, right? So it's the cosine, N2 is the component of N in the N2 direction. So it's the cosine with N1 x2, and therefore the area of that back face is the area of dA projected onto it through the cosine. Okay. And then so likewise, I have T E2. I'm sorry, this is N1, N2 dA minus T E3 N3 dA. All right, so that's the total forces, right? So that accounts for all these vectors. Tn times this area, TE3 times the area of the bottom, TE2 times the area of this backside, TE1 times this area. Okay. So then mass is density times volume. The volume of a tetrahedron is 1/3 the height times the base. So if the base is dA, the area of the base, so if the area of the base is dA, and the height is defined by this distance between the origin of my coordinate system and N, this is mass, okay? And then I'm just going to multiply by acceleration. F equals ma. Now you can immediately see that all the dAs, they're in every term, so we can cancel them. Okay? And if you remember in the beginning, when we talked about stress, I said stress is a point-wise quantity, right? So a point is an infinitesimally small volume, right? It's actually zero volume. So we have to take the limit as h goes to 0. So as h goes to 0, then this whole term goes to 0. And what we're left with is on the left-hand side. And so what we're left with, I'll write up here, is that. Now remember, these are all vectors in themselves, right? So like T n is a vector, so it's actually got 3 components. T1 in T2 in T3 in, right? And likewise for TE1, TE2, TE3. So remember, the thing in parentheses just identifies the surface in which that vector is associated with. And then the vector itself has 3 components. Okay? So if we were to write out all the components, what we're going to have is T1 in T2 in T3 in equal to T1 E1 N1 plus T E2 1 N2 plus T1 E3. Guess I lost my writing there. Okay, sorry. I'll just continue with, you already have T1 written, so I'll just continue with T2. And T3 Okay, and so with the additional T1 that I lost, and you can see this is nothing more than a matrix equation. Times N1, N2, N3. Okay, this thing is the stress. Okay, so technically it's a tensor, okay, but for the purposes of this class and the way we will use it, you can also just think of it as a 3x3 matrix. Please understand, I'm not saying that in all cases tensors and matrices are the same and that they transform in the same way. That's not true. For the purpose of this class, this is a second order tensor mathematically, but we can use it and transform it in the same way that we do 3x3 matrices. Okay? So typically when we then write the stress, we make the notation simpler. We drop these subscripts down so that these have two we drop the superscripts down to subscripts such that they have two components. So in other words, we'll have that S is equal to S11, S12, S13, S21, S22, S23, S31, S32, S33. And what those indices actually have meaning, we can see that on the next slide. So I wrote it as S. A lot of times, and S is probably more common in petroleum engineering and the geomechanics literature, but overall in mechanics, you'll often see stress used as sigma. Okay, it's probably if you took engineering mechanics, you probably what you saw, right? And so the visual definition of what those components are is the first subscripted component defines the face on which the vector acts. Okay, so back to our little infinitesimally small cube, the first component is the face. So for all of the ones on this face, we'll have a first subscript of 2 because it corresponds to the E2 direction. All right, so the first is the face, the second is the component direction, 1, 2, 3, which you can think of like X, Y, Z, right? And so I just have the notes there. The first subscripted index refers to the index of the unit vector that is normal to the face, and the second subscripted index refers to the component of the traction vector. Okay? So what the stress does, the stress tensor does, is it allows us to take any plane defined by a unit normal vector n and determine what the traction vector is on that surface. Okay? So I think we'll stop here. Next time we'll learn how to use those transformations on this tensor to simplify the whole problem even more.